Welcome to a deep dive into something really fundamental in the world of high-performance digital design. Today, we're cracking open the Advanced Extensible Interface. You probably know it as AXI.
AXI, right. The protocol everyone uses but maybe doesn't fully grasp all the nuances of.
Exactly. You've likely heard it called the digital highway, for solaces and FPGAs. It's robust, it's definitely fast, and it's basically how different blocks talk inside these incredibly complex chips.
It is the cornerstone, really.
But here's where it gets, well, really interesting. The very things that make AXI so powerful, like handling multiple operations at once, dealing with things out of order, they also introduce some unique and, frankly, quite tricky challenges.
Huh? Like deadlocks?
Right. Frustrating deadlocks, unfair resource sharing leading to starvation, and those annoying throughput bottlenecks that just slow everything down.
It's actually fascinating, isn't it? How striving for that peak performance can accidentally create these really complex ways for things to fail. So our mission today really is to give you a detailed look at these common traps. We want to trace them right from the basic protocol rules up to how they play out in complex system architectures.
Think of this deep dive as your shortcut. We want you to understand not just what AXI is, but also the disciplined design habits, the clever solutions, and the advanced verification you need to, truly master it. So let's dive in.
All right.
Okay, let's start at the beginning. What exactly is AXI?
Well, it's part of ARM's AMBA standard. Officially, it's a high-speed on-chip interconnect.
Right. Synchronous, burst-based, pipelined, built for high bandwidth.
Exactly. And critically, it's royalty-free. That's a huge factor in why it's everywhere.
A good point. So it's not just one single protocol, is it? It's more like a family.
Precisely. Its versatility comes from that family structure, each tailored for different jobs. First, you've got AXI4 full. That's the, let's say, high-performance big brother. It's memory mapped, supports bursts up to 256 beats. Ideal when you need massive throughput, like connecting to DDR memory controllers.
Makes sense. What else?
Then there's AXI4 Lite. The simpler sibling, you could say, also memory mapped, but crucially no burst capabilities.
Ah, okay. So lower bandwidth.
Much lower. Perfect for things like accessing control and status registers, simple tasks, smaller logic footprint. And finally, there's AXI4 Stream.
Stream. So data flow.
Exactly. It's the dedicated data carrier. High speed, unidirectional data flow, and completely addressless. Think DSP chains, video processing, anywhere data just streams through continuously.
So the differences are quite clear then. AXI4 Lite and Full have those 5 channels, AEW, WB, ARR, for going both ways.
Right, bidirectional.
While Stream just has the one T and only goes one way. Different bursts, addressing complexity. Each really is built for a purpose.
Absolutely.
Now the real fundamentals. How do they actually talk? AXI uses that parallel architecture of 5 independent channels. But how do they sync up reliably?
It boils down to a very simple 2-signal handshake. Valid and ready. The source puts valid high when it has information, and it has to hold it there until the destination says, yep, got it, by putting ready high. That's one transfer.
Sounds straightforward enough. But you mentioned nuances earlier.
Yeah.
Are there hidden gotchas even with that simple handshake?
Oh, absolutely. It seems basic, but there's a critical rule people sometimes miss. The source must not wait for ready before it asserts valid.
Wait, why not? That seems counterintuitive.
Because if the source waits for the destination to be ready before saying it has valid data, you can get into a dependency loop immediately. A simple combinational loop, potentially. It can lead directly to stalls or even deadlocks, right there at the most basic level.
Wow. Okay, so even a tiny timing mistake in how those two signals interact can just halt things. That's a big dependency on a seemingly simple mechanism.
It really is. And it's also super important to distinguish between a transfer, that single valid ready handshake, and a transaction.
Right. The transaction is the whole operation. Address, data, response.
Exactly. An entire burst of transfers. And AXI4 Full supports 3 burst types. Incrementing, where the address just steps up, like reading consecutive memory locations.
Like reading a book.
Yeah. Then fixed, where the address stays the same maybe for accessing a FIFO.
Okay.
And wrapping, which increments but wraps around a specific boundary, useful for things like cache line fills or circular buffers.
Got it. And these bursts, plus the ability to have multiple transactions going at once, multiple outstanding transactions and getting the results back out of order, that's the key to AXI's performance, right?
That's the core of its high-performance capability. But, as you hinted...
Here comes the double-edged sword.
Exactly. Those very features, multiple outstanding transactions, out-of-order completion, are what can lead us straight into our first major pitfall. Deadlock.
Okay, let's unpack this one. Deadlock.
Yeah.
There's a fundamental, it's when everything just
Yeah.
stops right.
Pretty much. It's when you have a set of processes, could be masters or internal blocks, that get permanently blocked. Each one is holding on to some resource, like bus access or a buffer, and is waiting for another resource that's held by another process in that same set.
Ah, the classic two trains meet at a single track crossing problem. Neither can move.
That's a perfect analogy. And for a deadlock to happen, 4 specific conditions must all be met at the exact same time.
4 conditions. Okay, what are they?
First, mutual exclusion. A resource, like a bus channel or a buffer, can only be used by one process at a time. AXI inherently has this.
Makes sense. One owner at a time.
Second, hold and wait. A process is already holding at least one resource while it's trying to get another one.
Holding the track it's on, waiting for the crossing.
Exactly. Third, no preemption. Resources can't be forcibly taken away. A process has to release its resource voluntarily. You can't just kick a master off the bus mid-transaction.
Okay, no stealing resources.
And fourth, the killer. There's a circular chain of processes where process A is waiting for B is waiting for C, and C is waiting back for A.
The snake eats its own tail.
Precisely. If all 4 conditions are present, you get deadlock.
So the interesting thing is, if you can break just one of those conditions, you prevent the deadlock entirely.
That's the key. You don't need to solve all 4, just prevent one.
Okay, so how do these conditions actually pop up in an AXI system? We mentioned the valid ready thing.
Right. At the most basic protocol level, yeah. A valid ready handshake violation can cause a stall that looks like a deadlock. Like if a slave insists on seeing WV valid, write data valid, before it asserts a ready, address ready, that just stops the write channel cold.
But that's maybe a simpler case. What about the more complex ones?
The really intricate and honestly more common type of AXI deadlock happens at the interconnect level, especially in those systems with multiple masters talking to multiple slaves, often through a crossbar switch.
Ah, the crossbar. Can you walk us through a typical deadlock scenario there?
Sure. Imagine a simple case. Master 0, M0, wants to write to slave 0, S0, and then it needs to write to slave 1, S1.
Okay, M0 must is 0, then M0 must S1.
Simultaneously, master 1, M1, wants to write to slave 1, S1, and then it needs to write to slave 0, S0.
M1, S1, and M1, S0. I see where this might be going.
Exactly. Now, what if M0 gets access to S0 and starts its transaction but needs S1 next, but M1 has already grabbed S1 and is now waiting for S0?
So M0 has S0, waits for S1. M1 has S1, waits for S0.
And since slaves usually handle one master at a time, mutual exclusion, and transactions can be long, hold and wait, and you can't just interrupt them, no preemption, you've just formed a circular wait. M0 waits for S1, which waits for M1, which waits for S0, which waits for M0 to finish its first transaction.
Boom. Total system freeze. Everything is waiting for something else that's also waiting.
Deadlock. And here's the kicker you mentioned earlier. AXI's very design philosophy, the features like out-of-order completion and multiple outstanding transactions, they directly contribute to making these scenarios possible.
Right, because they allow transactions to be in different stages simultaneously. That's the hold and wait.
And they create complex routing possibilities through the interconnect, which can accidentally form those circular dependencies. It's a fundamental trade-off. You push for performance features, you increase the risk of these complex interaction bugs.
So, for designers building these systems, what's the takeaway? You can't just connect things up and hope for the best. You need, what, specific architectural fixes?
You absolutely need proactive architectural solutions. One of the most widely adopted is what's often called the single slave per ID rule.
Single slave per ID, how does that work?
It's often built into vendor AXI crossbar IP cores. The rule basically says that for any given transaction ID coming from a specific master, all outstanding transactions with that ID must target the same slave.
Ah, so M0, using ID 5, can send multiple requests to S0, but it can't send a request with ID 5 to S0 and then another with ID 5 to S1 before the first one completes.
Exactly. It prevents that specific kind of circular dependency we described. M0 can't be holding a resource at S0 via ID 5 while simultaneously waiting for a resource at S1 using the same ID 5. It forces transactions with the same ID to the same slave to serialize in a way that breaks the potential circle. It also helps guarantee right ordering for a given ID, which is often critical.
Well, that makes a lot of sense as a preventative measure, but deadlocks can be incredibly subtle. How do you actually prove your design is free of them? Simulation seems like it might not catch all the corner cases.
You're right, they are notoriously hard to trigger reliably in simulation. You need more robust methods for high confidence. System Verilog assertions, SVA, are a great start.
Assertions. Like checks you right directly into the code?
Kind of. They let you formally describe expected behavior over time. You can write assertions to check, say, that a request eventually gets a response, or that valid-ready handshakes follow the rules. They run during simulation and fire immediately if a violation occurs.
Better than digging through waveforms later.
Much better. But for the really deep systemic issues like deadlock, the gold standard is formal verification.
Formal. That sounds heavy. Mathematical proofs.
Essentially, yes. Thermal tools use mathematical techniques to explore all possible states of a design or a specific interface without running simulation vectors. They can prove that a certain condition, like a deadlock state, is unreachable. It gives a very, very high degree of confidence.
Okay, that sounds powerful. Any other tools?
You can also use synthesizable protocol checkers. These are basically hardware modules, sometimes provided by vendors, or you can write them, that you instantiate directly in your FPGA or ASIC design. They sit on the AXI interfaces and monitor the traffic in real time during hardware testing or even in the final system.
Like an embedded watchdog specifically for AXI rules.
Exactly. They can flag violations as they happen in the actual hardware environment.
Okay, so we've got deadlock covered, the total freeze. But what about when things are running? Just unfairly. That brings us to the next pitfall, starvation.
Starvation. Yes. AXI itself, the protocol spec, doesn't actually say how multiple masters should share access to a slave or the interconnect. That decision is left up to the interconnect designer, specifically the arbiter.
The arbiter, the traffic cop for the bus.
Right. And if you use simple arbitration schemes, you can run into trouble, like basic fixed priority.
Where Master A always gets priority over Master B.
Yep. If Master A is always busy, always requesting the bus, poor Master B might never get access. It's starved.
Okay, that's obviously bad. What about round robin? That sounds fair.
Round robin is generally better. It gives everyone a turn. But even that can be unfair if masters have wildly different needs. Imagine one master doing huge long bursts while another needs frequent short bursts.
The long burst master could hog the bus for ages, even in its round robin slot, right?
Right.
Starving the short burst guy.
Exactly. So simple arbitration isn't always enough. This leads to that constant tension. How do you maximize throughput without being unfair?
So what are the smarter solutions?
Designers use more sophisticated algorithms. One common technique is an aging counter algorithm.
Aging counter, how does that work?
Each master that's waiting for the bus has a counter associated with it. Every clock cycle it waits, its counter increments. The arbiter then grants access not just based on priority, but it favors the master whose age counter is highest.
So the longer you wait, the higher your effective priority becomes.
Precisely. It guarantees that even a low priority master will eventually get access, preventing perpetual starvation. You see this in some systems like zinc socks.
Clever. What else?
Another approach, sometimes implemented as a separate module, is a burst equalizer, AB.
Burst equalizer. Does it chop up long bursts?
Sort of. It effectively limits the nominal burst size and maybe the number of outstanding transactions each master can request at once. It tries to equalize the impact of different burst lengths, preventing one master from totally dominating the bus bandwidth.
Does that hurt performance, though?
Yeah.
Adding latency.
It can introduce a small latency overhead, yeah. It's
Yes.
another trade-off. And then AXI 4 itself offers an optional feature, quality of service, QoS signaling.
QoS, like for networks.
Similar idea. The master can assign a priority level, a QoS value, to each individual transaction. The arbiter can then use these QoS values to prioritize more important or time-sensitive traffic over less critical data.
So the master can say, this one's really important.
Exactly. It gives the arbiter more information to make intelligent decisions beyond just round robin or fixed priority.
Okay, so multiple ways to tackle fairness. And you mentioned earlier, there's a connection back to deadlock here.
Yes, absolutely critical connection. Starvation isn't just about fairness or performance. A master that is starved, unable to make progress because it can never get bus access, can become the missing link that completes a circular weight dependency somewhere else in the system.
So the starved master might be holding a resource needed by another master, which is waiting for another, and eventually back to the starved one. But the starved one can never release its resource because it can't complete its transaction.
Exactly. So solving starvation isn't just about being fair. It's also a crucial defense against certain types of deadlock conditions. Fixing arbitration helps overall system stability.
Got it. Okay. Deadlock, starvation. Let's hit the last big pitfall, throughput bottlenecks. Even when everything is working correctly, no deadlocks, no starvation, sometimes you just don't get the performance you expect from AXI.
Right. You've got this high-performance bus, but your system isn't flying. Why not? Well, back to basics first. Incorrect valid-ready logic can absolutely kill throughput. If a master drops valid too early, before ready is seen, it forces stalls.
Unnecessary waiting.
Yep. But beyond the pure protocol, what other architectural things tend to limit speed?
Pipelining seems like a double-edged sword again. It helps performance generally, but
It can also create problems. A classic one is the ready signal path. Often, ready signals travel backwards through multiple levels of logic, and they might not be registered stage to stage.
so you get a long combinational path for ready.
Exactly. That long path can easily become the critical timing path for your whole design, limiting your maximum clock frequency. You can't clock the system any faster because the ready signal takes too long to propagate back.
Ouch. Okay, timing paths. What else? This might be surprising, but where do a lot of AXI-related functional problems like lockups and stalls actually come from in practice?
You know, it's often not the AXI interconnect IP itself, especially from major vendors. A huge source of issues, particularly system hangs and stalls, is actually in the software drivers controlling things like DMA engines.
The DMA drivers, really?
Right.
Not the hardware.
Often, yes. DMAs are complex beasts that bridge software and hardware, and their drivers are frequently buggy. We see specific pitfalls again and again.
Like what? Give us some examples.
Okay, a common one. Invalid transfer order. Trying to stream data into the DMA before the receiving channel, the stream-to-memory mapped S2MM channel, is properly configured and enabled. That often just locks up the DMA. You generally need to set up the destination, S2MM, before you start the source, memory map to stream MM2S.
Sequence matters. Got it.
Another big one, incorrect transfer length. The DMA might stall if the software tells it to expect, say, 1,000 bytes, but the hardware stream only sends 99. 8 bytes and asserts it last, the signal marking the end of a stream packet.
Or the other way around. Sends more than expected.
Or if last isn't asserted at the right time, or ever, the DMA just waits forever for data that isn't coming or gets confused by an early end of packet. Also, cache coherency. This gets people all the time.
Caches. When the CPU has its own copy of memory.
Exactly. If your CPU has data crashes enabled, the data the software thinks is in memory might not match what the DMA hardware actually reads from or writes to main memory. You get inconsistent behavior, data corruption.
You need to manually manage the cache.
You absolutely do. You need to explicitly flush cache lines from the CPU cache to memory before the DMA reads them, and invalidate cache lines after the DMA writes to them so the CPU fetches the fresh data from memory. It's tedious and easy to get wrong.
Definitely sounds error-prone. Anything else with DMAs?
Final common one, simple memory access errors. Software sets up a DMA buffer, but puts it in a memory region that the DMA hardware physically cannot access. Maybe it's in tightly coupled memory only the CPU can see, not main DDR RAM. The DMA transaction just fails with a bus error.
Okay, so the lesson here is
Yeah,
don't just trust the IP or the example code.
pretty much. A newer designer might look at vendor IP or examples and assume they're perfect. But an experienced designer knows the AXI protocol is an ideal framework, but real-world implementations, the Verilog, the drivers can have bugs, misinterpretations, or subtle issues.
So ultimately you, the designer, using these components, are responsible for making the whole system work, right? You can't just blame the vendor if the DMA driver hangs.
That's the reality. You own the final system integration and validation.
Okay, so putting this all together, if you want to avoid these bottlenecks and actually get peak performance out of AXI, what are the key proactive steps?
Right. Let's summarize the performance boosters. First, absolutely leverage burst transfers. AXI 4 lets you go up to 256 beats. That drastically cuts down the address control overhead per byte transferred. Use bursts whenever possible.
Minimize the overhead. Makes sense.
Second, exploit parallelism and pipelining. Use those multiple outstanding transactions. This is crucial for hiding the latency of slower peripherals like DDR memory. Keep the bus busy while the memory catches up. Out-of-order completion helps here too.
Keep the pipeline full.
Exactly. Third, use FIFOs or skid buffers strategically. Put them between modules that might have different throughput rates or timing. They help absorb variations in data flow and manage back pressure gracefully without stalling the whole chain.
Like shock absorbers for data.
Good analogy. And finally, going back to that timing issue, for deeply pipelined buses, seriously consider registering the ready signal at key points. It breaks up those long backward combinational paths.
Trading a little latency for a higher clock speed.
Precisely. It often allows you to meet timing at much higher frequencies, which usually results in better overall throughput, despite the extra cycle or two of latency on the ready path.
Okay, that's a solid set of performance tips. So we've seen the pitfalls, deadlocks, starvation, bottlenecks. We've seen some solutions. Let's try to bring it all together now. What's a comprehensive approach to prevention and verification look like? It feels like it has to start way back at the design concept stage.
Absolutely. It starts right when you're architecting the system. First, consciously choose the right AXI protocol variant for each interface. Don't use AXI 4 full if AXI 4 lite is sufficient, save the logic. Don't use memory mapped if AXI stream fits the data flow better.
Use the right tool for the job.
Exactly. And define things like burst lengths, data widths, and crucially, your transaction ID usage strategy early. How many IDs do you need? We'll use the single slave per ID rule and adopt a modular hierarchical design. Break the system down. It makes verification and debug much easier later.
Good design hygiene from the start. Then, during actual implementation, what's key?
Strict adherence to the AXI specification is paramount. Like, religiously follow the valid ready handshake rules. Don't get creative there.
Don't try to optimize the handshake unless you really know what you're doing.
Precisely. And master the burst addressing rules, especially ensuring bursts don't cross those 4KB address boundaries. That trips people up and can cause slaves or interconnects to behave unexpectedly. And embrace pipelining and skid buffers where they make sense for timing and flow control.
Okay, solid implementation practices. Now, verification. You said it's not an afterthought.
Definitely not. You need a multi-pronged verification strategy. Verification IPs, VIPs are a huge help.
VIPs. Those pre-built models.
Right. Companies like Synopsys, Cadence, Mentor, now Siemens EDA, and even AMD Xilinx provide these. They are pre-verified AXI master slave models and protocol checkers. They drastically accelerate test bench development and catch protocol violations automatically.
Saves a lot of time building your own checkers.
Huge amount of time. Then, leverage assertion-based verification, ABV, using system Verilog assertions, SVA. We mentioned this before. Write properties to check rules directly on your interfaces during simulation. It's far more powerful than just hoping random simulation finds bugs.
Catches bugs closer to the source.
Yep. And for those really scary systemic failures, like deadlock, again, formal verification is the heavyweight champion. If you can formally prove deadlock freedom for your interconnect or critical paths, that provides immense confidence that simulation alone just can't give.
So VIPs, assertions, formal, a layered approach.
Definitely. You need multiple techniques.
And inevitably, some bugs will slip through to hardware testing. What about debugging? AXI signals could be overwhelming.
They can. Your best friends here are good old waveform viewers connected to integrated logic analyzers, ILAs or equivalents, inside the FPGA or chip. Being able to capture and trace transaction IDs, valid ready signals, response codes, it's invaluable.
Seeing the signals in action.
Exactly. And here's a specific tip, especially for AXI stream interfaces, which can be a real pain to debug from a CPU since they're often not memory mapped.
Yeah, how do you poke data into a stream easily?
A really clever technique is to create a simple AXI Lite slave module that acts as a bridge. On one side, it has an AXI Lite interface the CPU can easily write to and read from, like registers. On the other side, it connects to your AXI stream interface.
Ah, so the CPU writes data to the AXI Lite slaves registers.
And the slave then pushes that data out onto the AXI stream output. Or it captures data coming from an AXI stream input and stores it in registers the CPU can read back via AXI Lite.
That gives you software control to inject and inspect stream data. Much easier than trying to control the stream source directly sometimes.
It simplifies debugging immensely by letting you isolate and control the stream interface using simple register reads writes.
That's a fantastic practical tip. Okay, let's try and wrap this up.
Sure. If we kind of zoom out, the AXI protocol, it really is this powerful, flexible foundation for modern hardware. It enables performance levels that were just unthinkable before. But as we've spent this whole time discussing, its advanced features, the pipelining, the out-of-order stuff they create, the very conditions for these complex failures, deadlocks, starvation, bottlenecks.
Yeah, it feels like mastering AXI isn't just about reading the spec, is it? It demands more.
Mm-hmm.
A kind of disciplined, proactive design approach. You
No,
have to anticipate these systemic problems.
you really do. And the architectural solutions we talked about, like single slave per ID or smart arbitration algorithms like aging, they offer clear ways to prevent issues right at the design stage.
Right. Design it defensively from the start.
Which then brings up that crucial question for you, the designer listening. How do you build systems that aren't just fast, but are fundamentally reliable? And the answer really involves embracing those advanced verification and debugging methods we discussed. Formal verification isn't just for specialists anymore. SVA, protocol checkers, these are becoming indispensable tools. By adopting this robust verification-centric approach, you can really harness AXI's power safely.
Build those high-assurance, high-performance systems without shooting yourself in the foot.
Exactly.
So maybe the final thought for you, the listener, is this. The principles we've talked about, anticipating failure modes, applying thoughtful architectural constraints, rigorously verifying complex interactions, these aren't just AXI-specific skills.
Good point.
These are fundamental truths for designing any complex, cutting-edge digital system. It's about ensuring that your innovation, your push for performance, doesn't accidentally become your Achilles heel. So go forth and design with confidence, but also with a healthy dose of caution and a solid verification plan.